evening, everyone. So welcome to my YouTube channel, Math Section. So today we are going to see third lecture on characteristics subgroup. So in this lecture, we will show that you take any subgroup of a cyclic group that is characteristic subgroup. Okay? So see the today's result. Every subgroup of a cyclic group is characteristic subgroup. So let H be a subgroup of a cyclic group G. We know that every subgroup of a cyclic group is cyclic. Therefore, H is cyclic, and let phi be an isomorphism of G. Okay. There are two cases. Either order of G is finite and order of G is infinite. So we are taking first case, order of G is finite. Okay. So when you have a order finite, we write like that. Okay? So let order of G is finite and that is n. Okay. Then G will look like a square up to a to the power n minus 1. And it is generated by generator A. Okay. We know that if G is finitely grouped and M divides order of G, then G has unique subgroup of order M. Okay. And this subgroup is generated by this. You take a to the power order of G divided by M. Okay. That means order of G by M. So order of G is n here. So it will be a to the power n by m. Now let order of H is m. Then H will be generated by this generator a to the power n by m. And what is order of H? That is m. So H is unique subgroup of order m. Okay. By previous lecture, characteristic subgroup lecture 2, we have that H is characteristic subgroup of G. Because in last lecture we have shown that lecture number 2, we have shown that if you have a subgroup, subgroup of unique order, that is always characteristic. Here H is a subgroup of order M, and that subgroup is unique. It means that subgroup has a unique order, that is M. So that is why it is a characteristic subgroup. Okay. So in this case, we are done. Now we are moving to next case. Order of G is infinite. Since G is cyclic group of infinite order, we know that every subgroup for a infinite cyclic group, the isomorphism group is nothing but I and T. T is nothing but it takes X to X inverse. There are only two elements in this group, isomorphism of G. So there are two cases. Phi is isomorphic. So either phi is identity or phi is T. So if phi is I, the image of H under phi is nothing but H. Okay. So if phi is T, then image of H is nothing but H inverse. Because H is subgroup or it is group. So it will be H equal H inverse is H. Okay. So in either case, either phi is I or phi is T, we have phi H is equal to H. So we have phi H is equal to H for any isomorphism of G. So what does it mean? It means that H is characteristic subgroup of G. Okay. So in this case, we also done. So finally, we have proved the result. Thank you very much for today's lecture. If you have any problem related to this, you can comment on my YouTube channel. Like, share, comment, and subscribe on YouTube. Thank you very much for today's lecture. Thank you very much.